Okay, so the topic for today is turbulent fluid flow. We covered laminar flow last week, and so we'll bump up the Reynolds number and look at how to do simulations of turbulence. And I found this nice picture by Leonardo da Vinci of turbulence. It was something he was interested in, I guess, one of many things. And so he's got this sketch of some flow coming in here and creating this this turbulence. And it's actually pretty insightful because what he's doing is he's got these little vortices here. So they're relatively large vortices, and then down in here there are smaller vortices, and then it looks like maybe this whole thing is a vortice or vortex of basically where the water is forming this swirling pattern. So as we'll see, that's an important theme with turbulence and something that we'll need to account for when we do the simulation. So I'd like to start off just looking at some examples of turbulent flow. There are some lab techniques that have been developed to image turbulent or flow that is turbulent, and here's some examples. One of the things we'll see is that the effect of a flow with an obstruction in it, and the obstruction then distorts the flow, creates a wake downstream from it. That's an important problem in this kind of fluid mechanics scenario, and we can think of it as a flow with an immovable object that the flow goes past, or we can think of it as relatively static fluid and the body is moving. And so what you see here is two dye traces, or two dyed or traced fluids that go past this body and mix. And we see these vortices. We also see kind of an oscillation downstream from this body. So we have kind of a general big picture pattern, but then these smaller vortices that cause complications. Here's an example from the lab where this laser fluorescence technique is used to image the flow, and we can see something done with very high-tech instrumentation that looks a lot like Da Vinci's sketch from 500 years ago. So this is obviously a way to get more data on the flow, but giving us essentially a confirmation of these this basic principle of these eddies at a range of scales. This is just a rising smoke plume, and we'll see a couple more examples of this, but what we're seeing here is down here at the base of the plume, a relatively smooth flow. This is laminar conditions right in here, and then we see as we go up and progress with increasing distance, the flow in this region is somewhat disturbed. There's perturbations in it, but it's not just we're not getting these real swirling vortices. But then once you get up into here, the flow is breaking up, and we're having this much more complicated pattern. And as that happens, you can see that that's also causing mixing. As this plume, it's changing width here. This is where the width that it starts out, and as it progresses up, we have an increase in the vortices and spreading as we get mixing of the plume with air, dilution of the plume, and a dispersion process. And then, my background is in geology, so I couldn't help but show this example of turbulent flow. And this is a volcanic eruption in Indonesia, and this is a ash flow, Nui Ardent type eruption. These things move at 100 miles an hour. So you can imagine that this person here is probably not really particularly enthused about their lesson in turbulent flow. But you can see at this scale, you have again these this complicated mixing pattern. Okay, so Kármán vortices. This is a kind of a special pattern of flow and turbulence that's associated with an object in the flow that perturbs the flow. And so here's a sketch from, or a picture from the laboratory where you've got this circular object. And what's happening here is that you have flow that goes around this object, and it goes around on one side, and then it's kind of an oscillation. It goes around on one side, and then the pressure field gets perturbed, and it then becomes more favored to go around on the other side. So it forms this oscillatory flow, and that results in this pattern of oscillations. And you can see that in a gross sense, it's kind of doing this. But if you look at it, zoom in a little bit, you can see that right in here, we've got a tighter swirl, and here's a tighter one. And then if you zoom in further on these swirls, this one, there's a vortice like that. But if you go in and look at it in more detail, there's a smaller one yet in there. Okay, so that's in the laboratory, and we see these things though in a variety of settings. This is a satellite photograph. Satellite photograph. Here's an island, and you can see these really pretty fantastic Kármán vortices being shed off of this island. And I don't know, for scale, it looks like this is hundreds of kilometers. Okay, so we've got this pattern of vortices that get shed off of this island. This is the largest scale one that I could find. These examples, including this one, are all a flow with an immovable object in it. But the same or similar thing happens when the fluid is relatively stationary and the object is moving through it. And this is an example of that. Here's some Kármán vortices that are shed off of this airplane. You can see this guy back here. And in this case, the vortices are shed are like this. There's one right in there. And they're shed all the way back like that. Okay, so as the airplane's moving along, they're coming off it like this. Okay, so it's a little bit different geometry than the kind of planar picture that we saw, but nevertheless, it's the same kind of process where we're having this alternating shedding of vortices off of alternating sides of a body moving through the flow. And so what we're interested in turbulence. So if we take a step back, we've got to be really interested in the whole spectrum from laminar flows, which we saw last week, to turbulent flow. And here, I guess we actually saw this slide last time where we've got this set of experimental results where it's a tube with dye that's introduced, and you get a nice straight line in laminar conditions. And then down here, this is fully turbulent, where you can see it's very thoroughly mixed, it's highly mixed from various vortices like that. And then in between, we've got this kind of a transition pattern where the flow is perturbed, and we might imagine there's like a vortex in here, but they're just kind of scattered through the flow. So it's not really down here. We've got the entire flow has these vortices through it at a range of scales, but here in this transition region, the vortices are forming, and then perhaps they form and die out, but they're kind of a scattered through the flow in this transition regime. And so here's the flow past a stationary object, and then here's the wake. And this is the flow past the circular obstruction, and this is the condition where you could get Kármán vortices, and you kind of see this vortex like that, but this is a much higher flow than higher Reynolds number than what we saw, and so you can see that the pattern in here is much more complicated. So we probably have much smaller vortices here than what we saw with those big undulating patterns downstream from in the previous slide. And then another place where we'll be getting this laminar to turbulent transition is along boundaries. And so here's some experiments that were done with flow, and this is the wall right here, and this is an entrance effect experiment like what you were working on for homework. And what you can see in this case is that right in here we have this laminar boundary layer developing, and then with increasing distance you can see that the flow starts to, right in here I guess, the flow starts to break up, and you get these turbulent eddies that form, and it grows, and you get larger and larger eddies, and this boundary layer grows like that out away from the wall. Okay, so here we have turbulence increasing with the flow direction, increasing with distance downstream, and this plume here, Humphrey Bogart shot, is a similar kind of thing where the plume is rising off the cigarette, and we've got laminar conditions here for a while, but then with increasing distance the effects of turbulence increases. And so we'll use the Reynolds number to characterize this, and we saw this last time I believe. The Reynolds number is a dimensionless number that scales the inertial and the viscous forces. So the key thing here is that the Reynolds number increases with velocity and distance, and it decreases as the viscosity of the fluid increases. So Reynolds number is increasing like this. Here's another set of experiments where the Reynolds number is increasing like this. And one thing that you see is that here these are low Reynolds numbers, and the fluid is injected like this, and what's happening in this case is the fluid is actually flowing like that. So you're having this kind of swirling pattern in this flow, but it's still under laminar conditions. So laminar condition doesn't necessarily mean that the flow is all just straight. You can have vortices forming, but there are these kind of stable vortices that are formed from the geometry of the flow. But what's not happening in this case, that is happening here, is that you have a whole size array, or a whole range of sizes of vortices. This kind of cascade of vortices from large to small that'll characterize the turbulent flow. Yeah, TJ.
Are there supposed to be V's in that, like two V's in the equation for velocity, kinematic, viscosity, so like another variable, like sub in, sub in?
What's that?
Is there like another variable I could use for kinematic velocity, or is that meant to be two V's?
Kinematic, this here?
Yeah.
Yeah, so this version of it, that's kinematic viscosity, and that's velocity.
Okay.
So kinematic viscosity is these two terms here. So the kinematic viscosity is equal to the dynamic viscosity divided by the density. So that's what this version is, just a little bit simpler, although usually, I don't know, usually I end up using the dynamic viscosity. So that's why I wrote it initially like that.
Yeah, yeah. I mean, the symbols of velocity and kinetic viscosity are very similar to each other.
Kinematic and velocity, yeah. Yeah. Yeah, I know. I think, yeah, so I think there maybe you can see it a little bit different. Not all that much different, but yeah, they are different.
Yeah, that's what I was kind of.
What happens, this is the software effect that it makes variables italicized, and so the V for velocity looks pretty good right there, but when it gets italicized, then it looks like the kinematic viscosity. Okay, so Reynolds number gives us a way to characterize the flow, and what we're expecting then is to have a low Reynolds number down here in the Reynolds number of 10, laminar conditions, high Reynolds number, this is 3,000. The details of just what these Reynolds numbers should be will depend on the geometry, but Reynolds number of 3,000 is turbulence, and then we expect then to have a kind of a transition region in between where we may get some vortices that are forming, but they won't be throughout the flow. Okay, so let's take a look at an experiment that was done in a tidal channel. So here's a map of the channel, and they put this fancy flow meter device here. So this is an electronic flow meter that will measure the velocity in different directions very quickly. And so they set this thing in here. This is a tidal channel, so the flow is varying varying with the tides, the kind of the bulk flow. And here's the velocity as a function of the tides. And you can see that, or this is a function of time. And so what you can see is that in general, you're having this kind of thing. This is the streamwise flow, so that's the velocity in the main direction of the flow. So you can see that as the tide goes in and out, it's increasing, the flow's increasing, and then dropping back. It's actually reversing, but this is like an absolute value of the velocity. Okay, so that gives you the big picture, but if you look at it in detail, you have other things. You have more than just that. You've got this stuff going on here, and so you might think, well, just kind of a low budget instrument, and it's just kind of a noisy instrument, and I can just go and average that out and get the result I want. And maybe so, but in this case, this is a precision instrument and made with high resolution, and these measurements are real. Okay, so this is what the flow is actually doing. And this is in the direction of the flow, and then this instrument can also measure perpendicular to the flow direction, horizontally and vertically, and the flow in these directions are less, but you can see that they're not zero, and they have this kind of a broad change here, but then this fluctuation that is that's happening as well. And so I think actually I've got another picture of this. Oops, don't do that. Yeah, so here's another picture of these data. The velocity as a function of time. This is over 60 seconds, and you could say, well, we average it out. There's the velocity, but this is the average. Say is around 2, but it's really fluctuating between 1.5 and 2.5. Okay, so the fluctuations are actually pretty large compared to the scale of the average flow. and that's the transverse and the vertical, and they're doing similar kinds of things. And so I think what would make sense as a way to characterize this is to say that the velocity is, what I think I'll do is use u for the velocity. So that's going to be equal to an average velocity plus a perturbation. So the average would be like this red line that I've drawn, and then the perturbation would be something like that. So if we took the red line here and added to it this guy, then we would get the observed signal. Okay? So we can decompose this signal into two things. The average, something that we might measure with just a more budget flow meter, and then this perturbation that's happening. And this is the perturbation is the result of these vortices that are happening in the flow. And if we start to look at the perturbations, you can see that we've got the perturbations are happening at a variety of scales. Maybe this is one here, kind of a large perturbation, and then here's one that are happening. That if we look at it in terms of, I guess, the period of the perturbation, we've got periods that are like this long here. That's, I don't know if the scale, that's maybe 5 seconds or so, and then you zoom in and you can see that there are even shorter period fluctuations, like right there or right there. They're just a couple of seconds. So we've got this perturbation that's happening over a range of scales temporally. And if we look at flows, and if we think back at the pictures that we saw, then we can also conceptualize the flows as, this is actually, here's 12 Mile Creek, which, you guys know where 12 Mile Creek is? It's just north of campus, and it's a really nice place. They just removed, a few years ago, they removed a couple of dams from 12 Mile Creek, and you've got now these nice rapids. So it's really pretty creek, and if you look at the flows there, you've got these vortices that are they're in the flow, and then on those vortices are smaller ones, and on those are smaller ones yet, and on down in scale. So we've got these perturbations that range over a wide range of temporal and spatial scales. Now, this is going to be important because we'll be interested in what the effects what effects these things have. So here's a summary, I think, of some of the things that we've seen about these turbulent flows. So as the Reynolds number increases, the flow becomes unstable, and you get these vortices that form. And if you start off with a laminar flow and you put a perturbation in it, you kind of drop you stick something in it, then the perturbations will damp out. But with higher Reynolds number, if there's some kind of a perturbation, that perturbation will grow and form this vortices. They're forming over a wide range of scales, temporal scales and spatial scales. And what happens when these things form is that you get some very rapid mixing. The mixing is mixing of mass, I think, pretty obviously, but also the momentum and heat, everything gets mixed within these flows. The other thing that we see is that we've got large vortices breaking up into smaller ones. We saw several examples of that. And I think one of the important principles here is what happens with the energy in the flow. If we have laminar conditions, whatever we do, we're going to dissipate some energy. So under laminar conditions, how do we dissipate, or what process causes energy to get dissipated in a laminar flow?
Friction.
Friction, yep. And what happens, what's the scale at which friction is happening?
Small.
What's that?
Small.
It's a small scale, yeah. So friction happens because of molecules kind of sliding past one another. And molecules slide past one another, and that's essentially heat, the motion of the molecules. The motion of the molecules within the flow is governed by, it's kind of characterized by viscosity. So our concept of viscosity is really the thing that is characterizing the energy dissipation from, at this molecular scale, from molecular motion, relative molecular motion. And that's how we dissipate energy under laminar conditions. Now, we bump up the flow a little bit, and we start to get these vortices like this thing here. So the vortices, that's going to dissipate energy as well, right? I mean, we have this big swirling packet of water, and that's going to take up energy. If we're interested in how much energy it takes to get fluid to go from point A to point B in a flow, if we have vortices along the way, those aren't really contributing to getting to point A to point B. They're just using up energy. So the vortices that we've been seeing are going to be an important component of the energy in the flow. And so what we can then think about, I think, is that we've got this system where we've got big vortices and smaller ones and smaller ones. And these guys are consuming energy, and they're doing that over a wide range of scales. And you can take these vortices on down to, we start off in a stream, we probably have vortices meter scale, but you probably look hard and see ones down in the centimeter scale, but you take it on down and they get smaller and smaller, and you take them on down to molecular scale. And so what you have then is, under laminar conditions, the energy is being consumed at the molecular scale from molecules sliding past one another. But then as you introduce turbulence, you have this whole cascade of scales from large eddies to smaller ones, on down to the molecular scale, where it's just really dissipation by viscosity. Okay? So that's the conceptual model. And at the molecular scale, we've got just molecular motion and heat, but then at larger scale, we've got these vortices. Okay, so how does that all manifest itself? Well, one way is just understanding the energy loss in flow. So we looked at this, I guess, 2 classes ago with this. So that's Darcy's law, and we can rearrange that to be like this. Okay, and so the energy in a flow, the hydraulic head is the energy density. That's how hydraulic head is defined. So the hydraulic head gradient that we have here from Darcy's law, that's how the energy is decreasing, or how the energy is changing along the length of the flow. So, if we have a tube here filled with porous material and a manometer and another manometer there, the hydraulic head is given by the height of the fluid in the manometer, and this height is decreasing along the flow, and that's energy loss in the flow. Okay, and in Darcy's law, we're assuming laminar conditions, so this energy is lost by the molecular motion that's characterized by the viscosity in the fluid. Okay? All right, so that's laminar conditions, but under turbulent conditions, we've got a variety of other laws. These are empirical laws that have been put forth to describe this relationship between the energy gradient, the head gradient, and the flow. And here I've listed some of them. The Mannings law, this is used to describe the head loss, or the relationship between the head loss and the flow in a channel. And it's written like this. This is how you usually see it, and it's the similar form to the way I wrote Darcy's law. But we've got there the head gradient is to the 1/2 power. Okay, so if you rearrange that, you get this. So this says that the head gradient is proportional to the flow to the power of 2. This says the head gradient is proportional to the flow to the power of 1. Okay? So Mannings' law covers flow in channels, like a stream. And it's essentially, if flow in a channel, it's essentially always going to be turbulent for practical applications, certainly for the applications that Manning was interested in. So this is characterizing turbulent flow. And what you see is that the head gradient is proportional to the flow squared. So a way to think about that is what happens when the flow, the way to think about it, I think, is what happens to the head gradient when the flow changes. So in this case, for Darcy's law, under laminar conditions, if I double the flow, then if I double the flow rate, then I double the head gradient. So if the head gradient is how rapidly the energy is lost along the flow, then I double the flow rate, I double the rate at which the head is lost. So that makes sense. But under turbulent conditions, if I double the flow rate, then I increase the head gradient by a factor of 4. Okay? So under turbulent, with Mannings' law, under turbulent conditions, increasing the flow causes a much bigger change in the head gradient than it does under laminar conditions. Okay? And the reason for that is because of these vortices that are formed in the turbulent flow. They're using up the energy, and they're causing this head gradient to increase much faster than it does with under laminar flow. Okay? So that's conceptually why you have a different in the exponent. This would have like exponent of 1 right there. Okay? That's that change in the exponent is from the energy that's used up by these vortices. All right, so Manning is for channels. There are a variety of others. This Darcy Weisbach, this is for conduits. This is pretty widely used to do the head loss in pipes, calculate the head loss in pipes. And what it says is this is the pressure drop. So this is written in terms of pressure rather than head, but still it's the pressure drop per unit length. And this is again from the friction or from energy, is from the dissipation of energy. And what it's equal to is, there's the velocity. So there's the velocity squared, just like we saw here. And it has, well, then there's these constant, there's the diameter of the pipe. So I wrote it here in a form that's going to be similar to what I've been using. And we see that we've got the squared term there, but we also have this F, Okay, this F is called the friction factor, and F, as it turns out, F is kind of a complicated quantity. It changes with the flow, and I'll show you more about that in the next slide. Some of the other similar kinds of flow laws that you might come across, the Weisbach law, head gradient, and it's just saying the head gradient is proportional to the flux to some power, which I think is consistent here. It's the power of 1 under laminar and 2 under fully turbulent. What happens in these things is that if you really want to cover the full range, under laminar is the exponent is 1 and turbulent, full turbulence is 2. In the transition range from laminar to turbulent, where you're having these little vortices form and just not completely consume the flow, they're consuming energy, and the exponent then is ramping up from 1 to 2. So this Weisbach law will accommodate that. The Forsheimer law, this is for porous media, and this says, well, I'm going to have two terms. I'm going to have this one here that's flow to 1 power, and then this one here that's flow to 2 power, and I'm going to characterize my flow that way. So this term here would do the turbulent component, and then this would be the laminar one. So what you end up with then is that the head gradient plotted here as a function of the flow. This is what you get for laminar conditions. Under turbulence, you have it rising more quickly. Okay, so that's a way to characterize the energy dissipation in the flow. And if all we're interested in is flow, is what the head drop or what the pressure drop in a flow would be, then something like this could be sufficient, providing that the flows are well, could be sufficient. Let's leave it like that. All right, so let's go back now to the Darcy Weisbach. Here's the Darcy Weisbach, and this is a flow and a conduit. The term here, F, that handles the effects of turbulence. Now, what you would like is for this relationship to work from laminar to turbulent conditions. So the people that are working on flows and pipes, they want to have a way to design the piping system, or to just understand how the head drops in pipes anywhere from over the full range of flows. So this was done with a series of experiments, and what they found is that at low Reynolds numbers, this friction factor was equal to this. At low Reynolds number, it's equal to 64 divided by the Reynolds number. Okay, so what that gives you is that the friction factor is equal to that, or you just substitute in the expression for the Reynolds number. All right. So if we do that, then we get that if we put this in there, that's what I did here. Just did that substitution. And so here's the friction factor. And you can see then there's some stuff that cancels out. So the density cancels, and importantly, this is velocity, so that velocity cancels with that. You end up with this, and simplifies down to that. Okay, so what you get then by having a friction factor that's equal to this, it gives you an expression where the head drop is proportional to, that's the velocity now, so proportional velocity of the first power, and it also has, it's inversely proportional to the diameter squared. This term actually ends up being analogous to 1 over the hydraulic conductivity. Okay, so this has the right kind of behavior for laminar conditions. but we want this to work under laminar and turbulent. So the way to do that is through this Moody diagram that describes the friction factor here as a function of the Reynolds number and the pipe, the roughness of the wall of the pipe. Okay, so you have flow down a conduit, and the surface of the conduit is going to play a big role in the friction. So what was done is Moody, I guess, was the guy who did this, series of experiments, and work out what this F term is at various different Reynolds numbers for various different types of pipes. So this curve here, right, like that, that's for a smooth pipe, and then these curves here, like that, are for a rough pipe, and the pipe roughness is characterized here along this axis. So the pipes are getting rougher in that direction. The pipe roughness is, I mean, you could imagine if you had a pipe that was made out of corrugated metal, then you would have a bunch of ridges on it. That would be a very rough pipe. Okay, so the way to use this is to figure out what the Reynolds number is and the pipe roughness, and that gives you then the friction factor that then you can use here. So this is nice. If you want to design pipes, it gives you a way to come up with what the pressure drop is. Let's try to look at it in a little more detail, though, and see what's going on here. So at low Reynolds numbers down here, the curve looks like that. And so that's, this is a log scale, so log scale. So that's proportional to 1 over the Reynolds number. So what we saw before, where the friction factor is 1 over the Reynolds number, that gives us a curve that looks like this. Okay, and that gives us F as inversely proportional to the flow. So down here in this regime, F is inversely proportional to the flow, and the head drop is then proportional to just to the flow to the first power. Okay, that's what we saw in the previous slide. But then look out here. Here, the friction factor is just a constant value. It's not related to the velocity, and it has a constant value. And in this case, out here where the slope is unchanging, then the head drop will be proportional to the velocity squared. And in between here and here, we've got these lines with various different slopes. And what that then gives you essentially is a head drop that's proportional to the velocity to some power between 1 and 2. Okay, so this is kind of doing this same thing that we saw conceptually, but with more different variables, with the pipe roughness, for example, that's included. We also see this kind of peculiar transition where you've got this effect. This is under laminar conditions, and then right in here, this is under turbulence out here, but right in here we have the Reynolds number. Actually, I guess it's, strictly speaking, it's just right in this range. That's the transition from laminar to turbulence, and there's this jump in the curve. And this is established from these laboratory tests. Okay, so the Moody diagram, it's an important aspect of designing pipes. It is a way of characterizing the flow, the energy loss in the pipe. And it was developed empirically. What we'll do for homework is we'll simulate this, and we'll show that we'll end up simulating the flow in a rough pipe at various different roughnesses and various different values of various different Reynolds number, and we'll get essentially Moody's diagram. Okay, so this is all on how turbulent flows have been dealt with by the engineers interested in, well, in this case, designing pipes. And so turbulence it's a very complicated process, but if you want to design pipes or deal with it in some of those other ones, the Ishbasher's law, that has been used for turbulent flow and groundwater. But those are kind of empirical approaches. In order to simulate turbulent flows, we need to, if we really want to simulate the full flow, then we need to take a bit of a broader approach. And there are really three methods that have been developed for doing this. And they're shown here, where we've got, this is a diagram where this is the scale from large to small. So this is large scale stuff, and this is small. And this is showing the how the energy is dissipated. So we've got large scale eddies here, smaller scale eddies, and then going down to very small eddies or just viscous dissipation. And these are three different methods of simulation. So this is one, and this is one. And what happens is that in this method, the DNS, or direct numerical simulation, this simulates all the different scales of the eddy. So we've got flows with big vortices in them, and all the way down to little tiny ones. So one approach for doing simulations of turbulent flows is to just go do it all. Simulate all of that stuff and get all of the gory details. And so that's probably the best way to do it. It ends up being, though, that's a lot of calculations, and so you can do small flows. It's very computationally intensive, basically. And so what's been done then is to come up with a variety of ways of simplifying that. And one of them is called large eddy simulation, and that's basically saying that from this scale here, we're just going to take this stuff and we're not going to simulate it explicitly. We're going to average it out, and we'll simulate explicitly the stuff at larger scales. And then this one, the Reynolds average Navier-Stokes, that one, it's a similar kind of thing, but the threshold is larger. So we have the averaging size right here, and all of this stuff we're just simply not going to solve for directly. We're going to lump it together and then account for it, basically account for the energy dissipation at smaller scales, but not show the pattern of flow that's formed. Okay, so there'll be three methods. I'll show you an example of these two, large eddy and direct numerical. We'll be working with this one, the RANS, or Reynolds averaged Navier-Stokes, but I'll show you these two others that are more computationally intensive. And yeah, so here's just a still picture of DNS where you've got this flow past, this is a square object, and you can see, zoom in, and this DNS is really allowing you to simulate all of the gory little details. Large eddy simulation is shown here, and you can see some eddies, but the smaller ones are just kind of averaged out. And the RANs would be a lot smoother than these two. I've got a video that, let me try going to. Well, Okay, so this is the large eddy simulation, and this is a back step. So this is flow off this this step here, and a tracer is put in the flow, and you can see then these vortices that are forming, swirling around, and then kind of they're tight right up here. They swirl around and spread out and are dissipating the energy. Okay, so this is kind of the intermediate scale resolution. This is, let's see. So here's the one that's higher scale. It's the same problem. This is direct numerical simulation. So it looks similar, but these guys are resolved. If you look in at, if you look in at some of the details, there are more details resolved in this flow. Okay, so this is fantastic. Computationally, this is fairly computationally intensive. And so for our purposes, we're going to focus on this Reynolds average method, okay? And so the Reynolds average Navier-Stokes, what this does is it's basically taking an averaging approach that is similar to what we did for porous media, where, you know, for lab we did pore scale flow, and for 2 classes ago we did porous media flow where we just lumped the pore scale calculations, or we lumped the pore scale variability together and really didn't consider the details. So for Reynolds average Navier-Stokes, that's going to be the same approach. And so I'm going to go and switch here. Okay, so let me show you how this Reynolds average Navier-Stokes works. So the thing that well, let's start off with just conservation of mass. So that's something that we've seen several times now. That's a principle that we're going to be comfortable with. And so if we start off with just our basic conservation equation, and we do conservation of mass, then cap theta is mass. So C is mass per volume. And that's equal to the density of in the flow. Okay, so this is conserved mass. So, so the storage term is just the rate of change of the density. The flux, we just have the advective flux, which is just going to be the density times the advective term in general is going to be velocity times c. That's our general expression for advection, and then in this case it'll be velocity times the density. And for conservation of mass, we don't have any diffusive terms. And we'll just say for our purposes here that the source term is equal to 0. We don't really have any source of mass in the flow. It's just flowing along. And that gives us this. So these guys substitute in, and the basic governing equation is okay, and so that's our starting point, and this is what we saw for laminar conditions. Now, for turbulence, the conceptual model that we've come up with, I think, by looking at these experiments and data is that the flow is equal to an average flow plus a perturbation. Okay, that was saying, well, if the flow looks like that, then we can say that there's an average and a perturbation, so that is equal to that plus that. Okay, and similarly, we would have the density is equal to an average plus a perturbed, and pressure, and so on. Okay, so that'll be the conceptual model. Pressure, we're not going to have pressure quite yet, but we'll get there. Okay, so we go here to our mass conservation, and we say that the velocity has this average component and a perturbed component, and so it's going to be this. Okay. Now, the next step is to say that we're going to average, oops.
I'm sorry, are those P's or rows?
Those are rows.
Okay.
Yeah. So it's just density and velocity right now. So the next step is we're going to average at AV, average over length and time. Okay, so so we've got some length scale like that, and we've got these vortices that are swirling around, and we're just going to take an average value over that length and just have a uniform value here. Okay, and that was what I was trying to get across on the previous slide, where I had the horizontal scale and we were saying, okay, we're averaging below this size. So we're averaging over a length scale, and also we've got this fluctuating pattern with time, so we're going to average over a time scale too. Okay, so we'll average over both. And so what I can do then is say, well, for that averaging, let me go and say, well, what I want to do is then average over, so that bar over everything is what I'm going to do to average. Okay, so in order to do that, we need to have some rules for averages. So if we do this, so this prime, this is the fluctuating component, okay? And so that's that. So the way that we've done this, though, is we've defined this fluctuating perturbation as it fluctuates about 0. So if we take the average of it over space or over time, then that's just going to be equal to 0. So that's going to be 0. If we take the time rate of change and the average time rate of change, that'll be equal to 0. And so if we have something like this, so we take the sum of the average density and the perturbed density. That will equal just the average density plus the average of the perturbed, right? And this is equal to 0. So that's just equal to, okay? So if we take the average of something like that, we just, the perturbed part just ends up canceling out. Okay, and we would have something similar for velocities. So what that gives us then is, if we go back to here and use this rule, these rules of averages, then we've got the divergence, and this average right up here, the average of this sum, it's just that just gives us the average. And this average of the sum just gives us the average. And this is just giving us the average. Okay? So this is actually not all that, I mean, this basically just giving us the same equation we started with. And so that's kind of cool. I think we understood where this came from. We did this averaging, we get this, and so it seems good. It doesn't seem like we're really getting anything different though. But nevertheless, this is where we start. This is mass conservation, and what we'll do is continue on and do momentum conservation. And so for momentum, we're going to, so this is mass, and now we'll do momentum. So we start with our conservation equation, and now the thing we're conserving is mass times velocity, and so C will equal mass per volume times velocity, or that's just equal to the density times the velocity. Okay, for momentum, we've got the advection of momentum and diffusion of momentum. Advection of momentum, that's just going to be velocity times c, and that's going to be velocity, and c is here, so velocity times density. Diffusion, the diffusive flux of momentum, is minus the stresses in the fluid. Okay, that's just what we saw last time, and so that allows us then to basically do the substitution. So we have F equals the divergence of the fluxes, which is there's the advection and there's the diffusion. So we have this guy and then we add to that okay? So there's conservation of momentum. So we good so far? Yeah? I don't know, I'm getting a little, yeah? All right. All right, so let's go back now to do the conceptual model perturbation. So U, it's going to be equal to a mean value plus a perturbed value. So each term has something like this. The density does too, but let's just assume that it's incompressible, so the density one we don't have to worry about. And Okay. Now we apply the average. So we got to average that, average, we're going to average, we're going to average that stuff, average that, average that. But before we do that, I want to multiply this term out. Okay? So, well, I can deal with this left side. If we apply that average, using those rules of averaging, we just get that. And now I'm going to write this out, and I get this. So we just expand this. So it's those two plus the average and the perturbation, and the average and the perturbation, and the perturbed, and then this is just going to average out to the stresses, and this one is going to just end up being okay. So everything has reduced down to just the average here and here and here, like it did last time. But this is where we have a bit of a difference. Now, we're going to apply the average over this whole thing. And what happens when we do that is this stays. I'm going to switch back. So this stays, and this will cancel because we're averaging this perturbation. So when we average the perturbation, then we have got that, and the average is 0. So that goes, and that goes. Now I have that. Okay? So these are actually the flows, the perturbations in different directions. And if these two perturbations are not correlated to each other, then each individual one averages to 0, but their product doesn't necessarily average to 0. Okay? That's the key. That's the key thing. And so these go, that stays. And you end up with this. And then I guess we had a density in here. And then I'm going to just write this term like that, the stress term. This divergence operator applies to that group and then to that group. So I write it like that. Okay, so here's what we end up with. That's new. And it's the product of the perturbed velocities. And it has the same units as stress. You know, in fact, we wrote it up here, grouped together with the stresses. So it behaves like a stress, and in fact, it's called the Reynolds stress. Reynolds stresses. And it's the UI, Uj times density. Perturb. Okay? So what we need to do is deal with that. It's a little bit of a tricky thing because we've introduced now a new unknown, new quantity that we have to solve for. And so the way that this is done is to recognize that the Reynolds stresses behave like the regular stresses in the fluid. And so we say that the Reynolds stresses what we saw previously was that the stresses in the fluid for just under laminar conditions, the stresses are equal to the velocity times the strain rate. That was what happens in a viscous flow. So what we'll say is that the Reynolds stresses are equal to a viscosity, a new viscosity times the strain rate. Okay, so what we said before was that the stresses in the fluid equal the actual dynamic viscosity times the strain rate. And now we're saying that the Reynolds stresses that come from these perturbed flows, that come from the vortices, that those guys are going to equal this, a term that is similar to what we had previously, except we've got this guy here. So this is the turbulent viscosity, or eddy viscosity. And so it behaves like viscosity. So I mean, it kind of makes sense. Real viscosity handles the energy dissipation at the molecular level. Eddy viscosity handles the energy dissipation from these eddies, from these circulating packets of water. So in order to proceed, we have to come up with a way to characterize the turbulent viscosity. So the way that we're going to do this, there are many different ways of doing this, and the approach that we're going to use is to say that the turbulent viscosity is equal to a constant times the density times this term. Okay? And K is equal to the turbulent kinetic energy and epsilon is the turbulent dissipation rate. Okay? So this introduces these two terms, K and epsilon, that we have to now deal with. So that's going to be the approach that we're going to use for characterizing turbulent flow. This is called the K epsilon method. The K and epsilon are determined. They are used to then characterize this turbulent viscosity, which then is used to characterize these Reynolds average stresses. Okay, so that's the general approach that we're going to use, and we'll be implementing it for homework.